Normalization and integral closures. So I remind about integral closure. Suppose you have a ring. So A is a ring. And it contains in B. It's contained in B. B, an element in this ring B. And we consider a submodel generated by B and its powers. So it's 1, B, B squared, B third, this submodel inside B. It's a submodel. And B is integral if this submodel, let's call it A of B. B is integral if this submodel is finitely generated. So, for example, you can consider A is Z, and B is Z of Gauss numbers, Gauss integer numbers. And then square of -1 is integral. Because the ring B is generated by it's Z square, because it's generated by 1 and square of -1. Okay, as a Z model. This is example of integral. And example of non-integral is you take Z inside Q. So this is your A, this is B, and inside Q you take B is equal to to 1 by 2, to a half. Then the corresponding Z model, so you have Z of 1 by half is not finitely generated because it sits in Q. And if it were finitely generated, it would be discrete in R. But it's not discrete in R clearly. I mean, it can be generated by one or several elements. So it's not, for instance, suppose it's generated by a number of elements, that then all denominators in this submodule are bounded from above, because they would all be expressed to a denominators of the generators. But they are not bounded from above. There could be denominators arbitrarily big, so it's not finitely generated. Generated over Z. So this was an example of non-integral element. Okay, and there was also a result claim that B is finitely generated if and only if B is a root of monic. Monic means that the leading term is 1. Monic polynomial over Q. Over R, A. In other words, you have B power n is equal to sum from I equal 1 to n b power I n minus I, AI, where AI belongs to A. N minus 1. Let's write it from 0 to n, and write here just I. Okay, so this explains why, what is the meaning of the finite generatedness. It's just roots. It's a bit like an algebraic number theory. Okay, also have integral closure. So it is a definition, the set of integral over A elements in B, which contains A, is called integral closure. Of A. Since they are all monic, their root, so they're all algebraic, but it's not sufficient. So all integral elements are algebraic, but not conversely. Sorry? So far, no, but at some point you definitely need it. This, let me explain why this, you mean this claim, or what? There was just one definition. Yeah, but domains, integral domains has nothing to, nothing to do with finite generatedness. Yeah, but let me explain. So how you prove this claim? So suppose that this is true. Then Bn is expressed through the lower degrees of I. Then Bn plus 1 is also expressed through the lower degrees, and so on. So one direction is clear. On the other hand, suppose you have this submodel is finitely generated. This means that it terminates. So you start with 1, then you add 1 plus, you add 1 and b, then you have 1 b squared, and so on. And it has to terminate because this model is finitely generated. And since it terminates, this means that at some point you would have Bn is equal to the sum of the rest. So it will be equal to this expression, Bi Ai from I equals 0 to n minus 1. So this is how this claim is proven. Thank you very much. Okay, the other observation which I did last time, I'm not going to repeat it because we had it with algebraic numbers and the proof is the same. That if you have two integral elements, you can add them and the sum is integral, and multiply this, the product is also integral. So this implies that this is a ring. So theorem, integral closure, is a ring. The point is that you can, if you have two roots of monic polynomial, then the sum is also a root of monic polynomial. This is standard in algebra, in Galois theory. So how you prove it, you just check that the model generated by the first is finitely generated. It gives you a subring, which is finitely, and then you add the second, since the second element, it's root of monic polynomials, it's finitely generated over the first or the second ring. So if you add two of them, it will be finitely generated over the first ring. So you do like iterate this construction. Okay, now the central notion which I'm going to explain for this, well, for a while because it's important, is normalization and normal varieties and so definition, or normal rings, or integrally closed ring. So ring A, so suppose it's a ring without zero divisors. Zero divisors. It's called integrally closed. What is the same normal? If the fraction field, K of A, fraction field, so if A inside this fraction field is integrally closed, is its own integral closure. So in other words, if the set of all integral elements x inside this K of A is equal to A. So A is its own integral closure inside that fraction field. This was originally defined in number theory because this is a natural assumption you want to ask if you expect to have factorial rings. And people wanted to have factorial rings because they wanted to prove Fermat big theorem, big conjecture, and it's very natural to prove it in assumption that certain number fields are factorial. This is something I will explain soon enough. Yeah. And this was the algebraic definition. Geometric definition is the following. It's actually better because for geometric, you don't need to assume your ring has no zero divisors. So definition, it's for, now I'm defining it for algebraic, well, affine varieties. So X inside Cn, affine variety is normal if X is disconnected union of Xi, which are Xi are irreducible, which is equivalent to having the regular functions without their divisors. And then all the rings OXI, this is rings of regular functions on the components, are integrally closed. And now we can characterize this geometrically. So claim X is normal if and only if all dominant finite morphisms from Y to X are isomorphisms. So dominant means that they are surjective on each irreducible component. And the finite means that on each irreducible component, the corresponding, birational. Finite morphisms, birational. Birational means that their fraction fields on each irreducible components are the same. Dominant? Dominant, it means that it's surjective. Dominant means that the corresponding morphisms of rings are injective. So it's something we had last time. Let me repeat it. It's important. Definition. X to Y is dominant. Well, last time it was a lemma, but I defined it if OY to OX is injective. Or what is equivalent, the image of the Zariski closure of the image of X in Y is Y. It's not obvious that that's the same, but this is something we did a lot last time, and I'm not going to use it, so I'm not going to repeat it. Okay, so this is injective, and moreover, on each irreducible component, there also they have the same fraction field. Birational means that it is an isomorphism fraction field on all irreducible components. And then it's finite. Finite means that O of X is, so what is finite? Finite means that O of X is finitely generated as O of Y model. So you have a subring inside fraction field which is finitely generated as O of Y model. It should be equal to O of Y because of the definition of integrally closed. Everything which is finitely generated and sits inside fraction field is equal to O of Y if O of Y is integrally closed. So this geometric characterization is equivalent to this characterization which is more algebraic, and to this characterization which is entirely algebraic. Is it completely clear? Sorry? Let me repeat. So let's restrict ourselves to just one irreducible component, because then you would just have a collection of irreducible components and you can do them separately. Let's restrict first to one irreducible component. So this means that you have an embedding of rings O of Y to O of X. Since it's birational, this means that they have the same fraction field. So your O of X is some subring in the fraction field containing O of Y. And then if it's finite, this means that it is finitely generated as O of X of Y model. And this means that by if O of X of Y was rationally closed, this means that here we have X to Y, so let's write here Y. Otherwise it becomes a mess. Okay, so you have your O of X is a certain subring in the fraction field of O of Y, which is finitely generated. It's equal to O of Y if O of Y was integrally closed. And conversely, if it is always equal to O of Y, then O of Y is integrally closed. So this condition is equivalent to being integrally closed. And then if you have several components, first you notice that you can just put your component apart. This is a finite map. So if you have two irreducible components, you can take x1 just union with x2 and map it to x, which is, and this would be finite map, birational. So, and we just prohibited all finite birational non-trivial maps. So this should be an isomorphism. This means that you would have this kind of decomposition, and then you check it on all the irreducible components. This is how you obtain from this definition this property, and conversely the same way. Yeah, xi should be reducible, so you do it for several components. Of course. Yeah, we never considered any non-reduced rings because they are all rings of functions on some affine varieties. So all our rings are reduced. Of course, you can do something with non-reduced rings, but this integral closure business has completely no sense. In fact, what people do in commutative algebra, they just assume your ring has no zero divisors. Unlike in algebraic geometry, where this really makes sense and it is useful to consider normal things which are not reduced. For the following, actually, there is a reason. It's quite funny. So first, you have this notion makes sense in, well, I'm doing complex analytic. There is a formal version of that. Let's do complex analytic. So normality makes sense for complex analytic varieties. You just consider the ring of complex analytic functions. You want them to be normal. So it's the same. And now you have this kind of variety. It is just a curve with self-intersection. It is irreducible. So normality makes sense. On the other hand, if you pass to a ring of germs in that point, it's no longer reducible. Unlike in algebraic situation, for complex varieties, when you speak of normality, you really have to include this kind of objects. So it's very natural to work with rings which have zero divisors. And the same in algebraic geometry, when you pass to completion, you would have the same phenomena. So in geometry, you have to do that. In algebra, no. In algebra, when you speak of normal rings, it's always without zero divisors. Okay, so this was the recollection of what we had last time. Now the new stuff. Yeah, before I finish with it, let me show you a couple of pictures. So there are two guys who are most responsible for this algebra, at least for this part of commutative algebra. It was Kummer. Kummer invented ideals. So for him, ideals were ideal numbers because he noticed that Sophie Germain, she proved, she believed she proved Fermat-Big theorem for all situations, but in fact, she used implicitly the uniqueness of prime decomposition, factoriality. Oops, sorry. There was something I didn't tell you last from the previous slide. Factoriality, so R is factorial. Ring R is factorial. If R has prime decomposition, unique prime decomposition, like in integers. There was a handout about this. Prime decomposition. And what is important that R is factorial, then it is normal. R integrally closed. So this is how integral closure first appeared. Should I explain this, or is it clear? No, not ideals. It's numbers, elements. of prime, and this decomposition is unique up to reordering and invertible multipliers, which can be decomposed. One of the definitions. Another is just can be decomposed. They're equivalent in that situation. But in a sense, you're right. For when this is wrong, when this is not true, the prime is not the same as indecomposable. There are indecomposable things which are not prime. Yeah, because it has unique prime decomposition. It's factorial. Any which is the root of a monic polynomial is integer. Yeah. Yeah, the proof is the same. It uses the same argument for all factorial rings. It doesn't matter. So I can give you the proof. It's not really hard. Okay, so let's use this. I will use the definition with monic polynomials. So I want to prove that it is normal. Suppose it's not. Then you have u quotient by v inside the fraction field of R, such that u quotient by v is a root of p. P of t is equal to t power n minus some ai t power I from I equals 0 to n. Then you have, this is coprime. You have u power n is equal to sum from I equals 0 to n minus 1 ai u power I v power n minus I. Right? This is divisible by u power n. They are coprime. So this is impossible because this is not divisible by yeah, so this is divisible by v. This is divisible by v. That every root of monic polynomial is integer. So you have a root of monic polynomial, u by v, and I'm proving that it is integer. We assume that u and v are coprime. U and v are coprime. Yeah, this is what I'm going to prove, that it is impossible. I'm going to prove that this is impossible. This is the point. Of course, there are rings where it is possible, very easy. I can give you an example in a moment. But let's figure out this. So you have u by v, which is a root of polynomial p. I wrote p, and I wrote this equation. This was u by v, but then I multiplied by v power n, and I obtained here something which is divisible by v, because all terms there are divisible by v. And this is not divisible by v. Moreover, this is coprime with v. This is impossible by uniqueness of prime decomposition. If something is coprime with v, u is coprime with v, then u power n is coprime with v. And then it can be divisible by v. And it is divisible by v because this is divisible by v. This is a contradiction. Yeah, and let me give an example. It's slightly, I tried to give this example last time. The problem is that I forgot what is. Okay, so our ring is Z of square root of minus 3. And then we have 1 plus square root of minus 3 by 2. And this is clearly, this doesn't belong to this ring, right? But I claim that this is a root of a polynomial. Let's write here minus, right? Then it will be 1 plus x squared equals 0, right? Right. So this is a root of monic polynomial, which doesn't belong to this ring. Then this ring is not normal. In particular, there's no prime decomposition, though there are lots of rings which are normal but don't have prime decomposition. This is very easy. But let me explain more, actually, about this. So this, let's consider a ring of Z generated by this element. It will be, actually, you can write it on the, this is a root of 1. So, and the whole ring will be, if you do like a regular hexagon, right? You can take the plane and tile it by regular triangles. It's a regular triangle, and the vertices of this tiling is precisely elements in this ring. And then you can use the standard arguments, which were in this handout, to show that this ring is actually Euclidean. It has division with remainder. And since it's Euclidean, by the same argument as proves uniqueness of prime decomposition for Z, you have uniqueness of prime decomposition for this ring. So this is less than 1, yeah. Yeah. And then if you just erase this every second vertex, you will come to this ring. It stops being Euclidean, and then the Euclidean algorithm in that ring fails because this is too big. This will be like a rectangle lattice with this square root of 3 and this distance 1, and this, it has no uniqueness. It has no Euclidean algorithm, it has no uniqueness of prime decomposition. Unlike this lattice, which is very nice and has uniqueness of prime decomposition. So you really need sometimes to add this 2. In fact, this was, I think it was something that Euler noticed. Slightly, I think he did this. Maybe he even did this error, because to prove the Fermat last theorem for the exponent of 3, so you want to solve an equation x3 plus y3 equal to z3 in integers. To prove that there are no solutions, he used this ring, and it had the uniqueness decomposition up to maybe this slight difference. And then he proved the Fermat for this exponent. And then Sophie Germain tried to to use the same argument for, she even wrote to Gauss that she had this solution, and she was almost correct. So then people realized that this uniqueness of prime decomposition so what she did, she considered the ring of integers where you add root of degree of P of unity. Here it was root of degree 3 of unity, and she added a root of degree p of unity to z. And she expected that it has prime decomposition, and she used that to prove Fermat. Since it doesn't have prime decomposition, it fails. In fact, now there is a notion Saint-Germain prime, which is a prime number for which this this ring has prime decomposition. And under 100, it's about half of the primes, I think, are Saint-Germain. But then it turns out that there is almost no, for big P, doesn't happen very rarely. So most primes are not Saint-Germain primes. In fact, I'm not sure one can even prove that there are infinitely many Saint-Germain primes. I think it's an open, maybe it's an open conjecture. So this fails. And this was noticed by Kummer, who realized that, okay, we don't have primes. There are not enough primes. Let's work with ideals. And he increased this, he strengthened the argument of Saint-Germain to include some of the rings, some of the primes for which the ring, again, there could be many ideals, but there's some prime ideals work well enough. This was the first step. And then Dedekind, okay, so this was Kummer. It was, I think, he did it probably when he was very young, maybe around 1840. And then it was Dedekind, who was, lots of postal stamps. Germans really like their mathematicians. Turkish are even better. They have a mathematician on the money. I think Germans also had Gauss at some point on Deutschmarks. But anyway, so Dedekind actually defined the rings precisely to solve this problem. And then he defined ideals, he defined the rings. Kummer didn't have definition, he was something more vague. And in particular, he had this notion of integral closure. It was, most of it was Dedekind. A bit of Kronecker as well. And Kummer, of course. Okay. So there's another important situation when you have prime decomposition, namely for polynomials. For polynomials of over a field, we already know this because polynomials over a field have are Euclidean ring. They have a division with remainder, which implies that they have prime decomposition as usual. But it turns out that you can have prime decomposition whenever you have polynomial ring. So if you have a ring with prime decomposition, the polynomials over this ring are again factorial, which is really convenient for many purposes. So the theorem, which is sometimes called Gauss Lemma, and I'm going to prove it, that R is factorial, then R of t also factorial. So then this gives you lots of examples, like integer of t are factorial, and all polynomials are factorial of n variables, and so on. So it's a good stuff. I think Gauss didn't consider this as important result. For him, it was obvious. So his claim, he was very young when he proved it, maybe 18 or 20. When he was a student, he discovered that you can, if you have Fermat prime, it's a prime which has a form 2 power n plus 1 or minus 1, plus 1, 2 power n plus 1, you can take regular polygon with this number of vertices and draw it with complex and ruler on a plane. So it was like a classical Euclidean geometry problem. You can draw a pentangle. It's something that people know. And then there are some ways of making polygon, regular polygon of 17 vertices. I think even that was unknown before Gauss. And then there are several Fermat primes. And the next Fermat prime is, I think, 64,000 something. And there is a legend that some graduate student in Göttingen spent 25 years writing his PhD thesis, which contained this, the way of drawing this rectangle with compass and ruler, this regular polygon with compass and ruler for these 60,000 vertices. And the whole thesis took like a whole cellar. It was several tens of thousands of pages. And it apparently, well, according to the legend, this manuscript is still kept somewhere in Göttingen. But probably it's all invention. Okay, so for Gauss, he wanted to do this classical Euclidean geometry stuff, and then on the way to this pinnacle, he used this factorial decomposition. So let me factorial this Gauss lemma. So let me tell you how it is proven. So So the first definition. Suppose you have R is factorial, and P of t is polynomial. And it is called P is primitive if the greatest common denominator of its coefficients is 1. In other words, this means that they are not divisible by anything except invertible numbers. Okay, and the first lemma, which is actually Gauss lemma, so in most textbooks, some textbooks call this Gauss lemma, but I think majority call the following lemma Gauss lemma. And of course, Gauss didn't give a proof. He just said that it's obvious that. It's factorial. It makes sense. Of course, it makes no sense whatsoever unless it is factorial. That's true, yeah, but we don't care. So lemma P1, P2 inside R of T are primitive. Then P1, P2. So P2 is primitive. A product of primitive elements is primitive. Greatest common divisor, yeah. So proof. Okay, let's take, suppose it's not primitive. If P1, P2 non-primitive, there exists a prime. P inside R, this is small p, such that P1, P2, they're primitive, they can be 0 modulo P, but their product is equal 0 modulo P. Consider P1 and P2 modulo P. They are polynomials in R quotient by P of T. This is a ring without P is a prime, so this is a prime ideal, and this is a ring without zero divisors. You have two non-zero polynomials in a ring without zero divisors, their product is non-zero. So P2, P1, P1, P2 is non-zero in this ring. Because the product of two non-zero polynomials is non-zero, which you can prove by induction. Just take the smallest non-zero coefficients of the first, the smallest non-zero coefficient of the second, you multiply them, you take the smallest non-zero coefficients of the product, it will be the product of these two coefficients, and this has non-zero divisor, so it's non-zero. Okay, this is the proof. So it cannot be divisible, the product cannot divide P because of this argument. Okay. There's a second lemma which I'm going to use now, before I prove this Gauss theorem. It's about reducibility. It's a consequence of the theorem I just gave to you. It's about reducibility of polynomials in the fraction field and in the ring. So suppose, let's K be fraction field of R, and you have P of T, it's a polynomial, which is primitive and irreducible in K of T. So it's irreducible as a polynomial over the fraction field. Then this polynomial, P of T, is irreducible in the whole ring. Of course, if it is irreducible in this, conversely, it's irreducible in R of T, then it should be reducible in over the ring, over the field. Because, of course, if it is irreducible over the field, it will be reducible over the ring. But converse is not obvious, because irreducibility, if it is, you have written this polynomial as a product of two polynomials in this over this field, then you have to make these coefficients integer, and a priori they are not integers. So you have to prove it. Okay, so you have and it is big K here, so let's do it big K. So it will be big K. Okay, by absurd, suppose that P is not irreducible, so P is equal to P1 times P2 in the fraction field, in the polynomials of a fraction field. I want to make it integer, so I do it, I write S1, S2 as greatest, as a common denominators of coefficients of P1, P2. So I write P1 and P2 as some elements in the fraction field, and I write them as fractions and take the denominators on these fractions. Okay. Then we have now an expression in integers. So you have your RP is equal to S1, S2. These are our common denominators of the coefficients, P1, P2. And R is obviously their product. P prime, P1 prime, P2 prime, and we can assume that P1 prime, P2 prime are primitive. If they're not primitive, we just increase this S, we move this to S. And also we can assume that R is coprime with S1 and S2. If it's not coprime, you just divide by the corresponding divisors, and you arrive at the situation when it is coprime. Okay, then the product P1, P2 is also P1 prime, P1, P2 prime is primitive by lemma 1. And this means that the greatest common divisor of coefficients of P1 prime, P2 prime is 1. But S is coprime with R. This is a contradiction because S is coprime, S1, S2 is coprime with R. And this is primitive, so this product has no common, so the common divisors of the coefficients of this polynomial are 1, and common divisors of this product are S1 and S2. But S1 and S2 are coprime with R, then R is invertible. And this means that P is S1, S2, P1 prime, P2 prime. We just proved that every polynomial which is irreducible in the ring R of T is also irreducible in the corresponding field of fractions by going to, it's not irreducible, of course, but this was the argument by absurd. We assume that it is not irreducible over the field, and we prove that then it is not irreducible over the ring. Am I clear? Completely? Please ask questions if I'm doing something which is not clear. Okay. Yeah. Now we can prove this Gauss, the main statement, the Gauss Lemma, which is this theorem. It's very easy, in fact. So K is but it uses the fact that the ring of polynomials over a field is factorial. So you have a irreducible decomposition of so you have a primitive polynomial P of T, a primitive polynomial. If it's irreducible, we are done. Suppose it's, yeah, we want to decompose it as onto a product of primes and prove that this decomposition is unique. We can do it over a field. So P of T is a product P1 times and so on times Pn of T in K of T. And this decomposition is unique. after permutation and multiplication by invertible elements in R. Now R is K of T, so it's a field, so it's just unique after permutation. But then this decomposition actually gives you a decomposition in by lemma 2. It is integer by lemma 2. This P of T, after you rearrange the denominators a bit, we'll obtain that P of T is equal to P1 dot Pn, where all Pi are integer, are in R of T. Because every decomposition of polynomial into a product of two reducibles is actually induced by decomposition in R of T. This was lemma 2. Okay, this is the uniqueness what you want. Yeah, and then we have some corollaries. So the first corollary is that since Cn is spectrum of polynomials T1 over Tn, and this is factorial, the Cn is normal. This is the first consequence, and the second is you can start with anything which is already factorial. So you start with x such that OX is factorial. Then O of x times Cn is O of x is polynomials over O of x, T1 dot Tn. This is something we had already done. So the product corresponds to tensor product, and if you take a tensor product by polynomials, it's the same as you take polynomials over this ring. And this is factorial, so this implies that x times Cn is normal. Of course, the normality is much weaker than factoriality, but for many practical situations, they're equivalent. For instance, if you work in dimension 1, so if you work with curves in Cn, dimension 1 subvarieties, then factoriality, locally at least, is equivalent to normality. But it's not for global, it's for, well, we shall go to that later. Anyway, it's useful stuff. Any questions? Yeah, this is really important, yes. So what is, as another consequence, you obtain that if you have a codimension 1 subvariety in P, well, it takes work, but you're right, yeah. If you have a dimension 1 subvariety if you have a divisor in Cn, which is irreducible, it will be prime. In fact, all divisors are principal. There was last time a notion of principal divisor, and what this theorem also implies is that all divisors in Cn are principal. Yes, thanks. It's an important, but I'm not having time for that. I will show you a couple of pictures of Gauss, and then we'll have an interval. Okay. This one picture of Gauss. I don't know what the source of this picture, but I found it as a puzzle. So Germans can go to the shop and buy it as a 1,000 pieces puzzle, and then make a puzzle of Gauss. Complete a puzzle with Gauss. I think this is the same picture. Well, and then this is the book. So Gauss wrote it when he was 20 or 21, and published it when he was 24 in Latin, and it is a book which has this Gauss Lemma, more or less in modern terms, except that it has pretty much no proof, because for Gauss it was obvious. Okay, so we have an interval for 5 minutes. Nós temos intervalo para 5 minutos. Okay, so the important thing is that you can in fact prove that normalization exists and it is finitely generated if your ring is finitely generated. It's not trivial. Today I will prove part of it, that if you have a integrally closed Noetherian ring and you have its finite extension, then the integral closure of the set of all integral elements in this finite extension is also finitely generated. So the aim is to prove that whenever you have a ring which is finitely generated, its integral closure is finitely generated. It's not obvious, but at least part of that can be done today. The rest would take more commutative algebra. We need things like Nakayama lemma and so on. And even that, what I'm going to do now is non-trivial. It takes, the argument is almost entirely number theoretic, like Galois theoretic. It uses trace, just like the argument we used last time with the Galois theory and primitive elements. It was based on trace, and now this argument is also based on trace. So theorem. Suppose you have A inside B. So A is it's a subring, and then the corresponding ring of fractions, K of A. Or you can consider K of B as extension of K of A. It should be a finite extension. And then we assume that A is integrally closed. And then you can take, if B is not integrally closed, just replace B with integral closure. So let's assume B is integrally closed, is integral closure. Yeah, when you say integral closure, integrally closed is integral closure, but here it's, you see, B is integral closure of A inside K of B, obviously, right? Otherwise, it makes no sense. Then B is finitely generated as a model. Algebraic closure is integral. Well, what is algebraic closure? It's infinite. It's every element of algebraic closure is integrally closed over the field. Because if you work with the field, that integral closedness is the same as just algebraic finite extensions. So an element over a field is integrally closed if and only if it is contained in finite extension. But this is not interesting because we are interested in that. So why this is needed? This is needed because in number theory, for instance, what you want is you want to have a ring of integers. So suppose, I will just give an example immediately because this is something that people always do. Suppose you have K, it's finite extension of Q. Then K is called arithmetic field, and you have arithmetic ring, or K is integral closure of Z in K. So this is an example. And by this theorem, let's call it theorem 1, for instance. Theorem 1 implies that OK is finitely generated. Over Z. Well, this just means, because it's torsion-free, this just means that it is Zn as a Z model by classification of... Z models are the same as abelian groups. So this, because all finitely generated abelian groups without torsion are just Zn, this would be Zn as a abelian group. And this, of course, where all number theory starts, because then you consider the generators, you start working with these generators, and you define things. Okay. So let's start the proof. Step 1. We have B inside B, and we define LB. It's a multiplication. It takes, for instance, is K from K. So it belongs to endomorphisms of K big over K small, where K big, let's use the notation, K big is K of B big, and K small is K small of A big. And it takes LB of A is equal to AB of B prime is BB prime. So it's an operator of multiplication by B. Yeah, we define trace. Trace of B is trace of this operator, considered an operator in K. So it's a trace of this corresponding matrix in this fine dimensional. So this is fine dimensional space over K small. So we define a trace, it belongs to K. We consider LB as a matrix over K big. It's finite matrix, and by n we take its trace. It makes sense. It doesn't matter which basis you take, it's still well defined. Okay, now I claim that in fact it belongs to, in fact, trace K of LB belongs to A, to the integer part, because okay, you take the characteristic polynomial of you start with the basis. You can find a basis which is such that since B is finite, belongs to finite submodel of finitely generated submodel of B big, this means that you can have a matrix on certain basis. The matrix of B has coefficients in A. LB has coefficients in A. Yeah, you can, in the slides I did it with characteristic polynomial, but the idea is that you can express characteristic polynomial of B in terms of the, it's slightly more invariant. You can, it will be matrix with coefficients on B, and you can take its derivative of this characteristic polynomial, it will give a trace. Doesn't really matter. So what is important is that you have a basis in B for which generated by B and its powers, and all its coefficients of the matrix given of LB in this basis belong to A, just because B generates a finitely generated A model. Okay. So here the argument is based on the Cauchy-Hamilton theorem, which says that if you take the characteristic polynomial, if you write the characteristic polynomial P of t is equal to determinant of t identity minus LB, then P of LB is 0. And then you can use it to prove that coefficients are integral over A, and then A is integrally closed in itself. So, but I think this is easier. Okay, the other observation is that trace is irreducible, is non-degenerate. Step 2. Okay, so you have a basis in B such that LB acts on this basis by matrices which has coefficients in A. Then its trace is integer. On slides, it's a more complicated argument, which we definitely don't need now, but you can try to think about how you can use the Cauchy-Hamilton theorem, this one, to prove that the same argument, the same statement. Yeah. Now you have the trace form. Trace form of xy is by definition equal to trace of xy in that sense, and it's non-degenerate. It's not degenerate, a-valued form on B. Non-degenerate because trace of x minus 1, x minus 1 of course doesn't need to belong to B, B is a ring, but it belongs to the fraction field, is trace of 1, is just dimension of k big over k small. This non-zero. So for each element x, there exists something. Well, you can always take it, multiply it by denominators so that it belongs to B, say that the product is non-zero. So trace is non-degenerate. Okay, step 3. We take a basis, E1 dot En is a basis in K over K small. And then we take again the minimal polynomials. Py of t, they belong to K small of t. K small is the this fraction field. It's minimal polynomials of EI, of the basis vectors. Okay, so we have P of t. We can write it explicitly. Pi of t is a I t power ni plus terms of less or smaller order. Sum of j less than ni a ij t power j, where ai they belong to a. This again is because minimal polynomial of an element in so the coefficients belong to a. Of course, they belong to fraction field of a, but you can multiply your generators by a number sufficiently big so that it becomes integer. Or you can just multiply the coefficient, doesn't matter. Then what is important is that ai ei has coefficients, has monic characteristic polynomial, minimal polynomial. You just replace, this is a big. Yeah, you just plug this into that and you divide by ai power ni. Okay, and the polynomial p tilde I of t, I'm just writing this polynomial explicitly, is equal to t power ni plus sum, again, for all j less than ni, we take a ni minus j, a ij t j. This is just explicit form of the minimal polynomial for this element. Oh, yeah. And this, of course, implies that, look, it's a monic polynomial. So they all belong to ei. So now replacing ei by ai ei, can assume that all ei belong to B. So you have a basis for your field K, which sits in B. So this is sort of clear. You have an element. It has a coefficients of these polynomials are, of course, not elements of its minimal polynomial, are not elements of A. They are element of fraction field. But then you just multiply this element by the smallest common denominator, by all denominators of these coefficients, and this gives you element now which has integer coefficients for the minimal polynomial. Am I clear? Clear? Completely? Should I repeat? Okay. We're almost done anyway. Of course, this basis doesn't give you the whole B. It's much smaller. So so now it's step 4. Step 4. you have E1 dot En inside B. They don't generate B. And of course, we want them to generate B because we want B to be finitely generated. They generate some small submodel. They generate B1 inside B. Define B1 star. It's called here M, so maybe let's call it M. But it is dual. It's a set of all set of all B inside K big such that trace of B multiplied by EI belongs to A for all I. So it's like a dual. For instance, if A were integers, this would be an integer valued form, and this is just a dual submodel, like a dual lattice. Of course, it's much bigger because clearly B belongs to M. This is because all elements of elements of B, their traces belong to A. And if something belongs to B, you multiply it by EI, the product also belongs to B, so the trace belongs to A. So if we manage to prove that M is finitely generated, we're done, because this would be a submodel of something finitely generated. Did I write it? This is Noetherian, I should. A is Noetherian. I mean, we almost never work with non-Noetherian rings. If I forget to write something about something that it is Noetherian, it's like 90% that I just forgot. So you have, look, B is contained in M. If we prove that M is finitely generated, then B is also finitely generated because you have Noetherian ring, you have finitely generated model, every submodel is also finitely generated. So this is why we needed A to be Noetherian. This is the only place we use Noetherianity, but it's significant. Anyway, we never had any non-Noetherian rings. It's really rare. Okay, so this is what we need to show. That yeah, but its generators are so let's write its generators as follows. So this would be step 5. Is EI star. It's a map from K big to K small, which takes EI, EJ, and maps it to delta IJ. So in other words, it takes EI star of EJ is equal to 1 if I is equal to J, and 0 if I is not equal to J. This is well defined. And moreover, M is generated by EI star. It's just dual space. It's nothing to, I mean, it's straightforward. So we have our model, which is finitely generated. This was a submodel of B. It was finitely generated model, generated by EI. And the dual model, which contains M, it's also finitely generated, because it's dual. I mean, it's standard. If you have a basis in a space, you have a basis in the dual space. The same for models. And then n is just a power n. And b is contained in m. By necessarity, b is finally generated. We're done with the proof. So this sort of ends the story when you work with number theory, but it doesn't end the story when you work with finally generated rings, because, I mean, for number theory, you just always work with fields which are finite extension of Q. And then you can apply this theorem and prove that normalization is finitely generated, but of course for algebraic geometry, you need bigger rings, which are quotient of polynomial rings, where this can't be applied. So we need more. And we'll have it after a while. But let's do corollary. So, so the first corollary is about the rings which are like you have finite morphism to Cn. Finite dominant morphism to Cn. So corollary. So we have A is a polynomial ring, C of T1 to Tn, which is O of Cn. And B is finite extension. So B is K of B over K of A is finite, and A sits inside B. So this would imply that the corresponding map is finite on the level of, at least on the level of fraction fields, it's finite extension. Then the integral closure of B is finitely generated. Okay. And the proof uses actually factoriality. So proof. So A is factorial. Then it is integrally closed. Then you can apply this theorem and obtain that, well, we can assume here that B is integrally closed, but let's denote it integral closure B1 and apply this to B1. B1 is finitely generated as a model. And this takes care about lots of examples, because in fact, many varieties can be realized as ramified covers over Cn. And then you have this nice picture. But I'm not going to do it before we did. So this statement is called Noether normalization lemma. It sort of gives you a parameterization of algebraic of affine variety by a ramified cover, like a cover of Cn, which has ramification divisor somewhere. It's a bit like Riemann surfaces, which is ramified, which admits ramified covering to C, similar to this classical Riemann surfaces arguments. Okay, now we can define normalization. Definition. Suppose you have a affine variety, and suppose that you have O x sits in K, which is K of OX. It's a fraction field, affine irreducible. And suppose that integral closure of OX in K is finitely generated as a ring. Of course, a posteriori, it will be even finitely generated as a module over this ring, but this is something we don't know, and in fact, the proof would also imply that it's finitely generated as a module. Then, let's use notation for integral closure. Here it's called A hat. So this is called A, and integral closure is A hat. Then the spectrum of A hat. This is the algebraic variety, which is affine variety, which is associated with A hat by Hilbert-Neustein and Zatz, which gives you equivalence between varieties and affine varieties and a finitely generated field. It's called normalization of X. And then I will prove that it always exists. So in 2 or 3 lectures, we'll prove that A hat is always finitely generated later. Ok, thank you very much. Muito obrigado. Eu termino.